and I know we have a very good reputation in this area, and probably it's right where either drawn out of were attached to the math department like we have it here, or perhaps attached to the EE department. I think in Stanford, I think it's originally part of EE. And but today, we look at computing and computer science sort of really taking over everything. And perhaps today, a new university would probably form computer science as the first department and perhaps go EE out of it. And the smartphone is a kind of example of that. All of you, many of you have these phones in your pocket. It's essentially a very large computer. It probably has about at least a dozen processors. Some of them are running, clocking at very high rate, 200 megahertz, 400 megahertz. And what it is fundamentally it has antennas to talk to pick up, transmit or receive RF radiation across multiple technologies, 2G, 3G, perhaps even 4G, wireless, Bluetooth, Wi-Fi, NFC, near-field communications. And then it has other transducers like multiple microphones, it has speakers, it has multiple speakers, and of course it also drives displays for presentation media, and it also has haptics by which you can you can pick up strokes of your palm or of your fingers and then understand, take inputs from your fingers. So it's really a bunch of transducers with a large computing engine inside it. And the amount of computing in a phone like this today probably would equal the computing of a large enterprise 20 years ago. So it's really incredible that we can do all this in a phone. So a number of the technologies involved here, the phone are from signal processing, signal transmission and reception, image processing, voice processing, lots of compression, decompression ideas, security. So a huge number of technologies, all largely implemented either by special purpose, by general purpose computers or special purpose computers. And people who build phones are, in some sense, largely computer architects. People who have computer architecture understanding of algorithms, understanding of voice processing and image processing and so on and so forth. Many of these things I'm sure you do at this institute. So with this, a phone like this has a number of ideas inside it, and many of us have contributed ideas which have actually gone into practice. And some of those people are here sitting in this audience, and I will talk about 4 of my ideas, which not all of them have got into phones, at least 3 of them have got into phones. Okay. So I'm going to start with, my 4 ideas I'm talk about is estimation of Markov processes in noise, which actually was my PhD thesis at IIT Delhi. Second one will be on an algorithm called Esprit, estimation signal parameters using rotation variance technique. And the third one is MIMO, and then the fourth one is called MIMO OFDMA, which is the underlying technology of 4G. And I'll talk a little bit about the lessons that one can draw from how these ideas came and how they evolved, and say a little bit about innovation in the Indian scenario. Next slide. So the idea of estimation of signals and noise has a long history. And the basic idea is you have an observation, which is sort of a signal of interest. It could be in a direction of an aircraft, or it could be anything. It could be a voice signal, which is corrupted by noise, additive noise. And the first person to look at this problem was really Carl Freddy Gauss, a real genius, who developed method of least squares. And this is back in, I think around 1800, late 18th century, 1790. People were based on Kepler's work, people felt there must be a planet between Mars and Jupiter because of this Kepler's idea of this perfect solids. But actually, that theory was wrong. But nevertheless, people were looking for it, and an astronomer called Piazzi discovered there was a small planet, minor planet, we don't call it planet anymore, which is called an asteroid, just named Ceres. And he tracked it down a little bit made some measurements on it. And then it disappeared behind the sun, so we couldn't see it. So Carl Gauss took some of the measurements, and using method of least squares, method of fitting, he was able to predict when the planet reappeared behind the sun. So that's the first time The idea of when you have some signal of interest in noise, how do you minimize the effect of noise and maximize or get the best estimate of signal was actually done by Carl Gauss, because he was a real genius. And then it took 140 years when Norbert Wiener, another genius, who working at MIT, was involved with design of fire control systems and radar tracking systems. And he came up with the theory of extracting signals from noise. The signals were modeled as stationary signals. The statistics were not changing for stationary. And he described the signals in terms of covariance functions. And so that was well known, and many of you who learn estimation theory, signal plus additive noise. And you're interested in estimating the value of the signal at time t, which could be at same point at S, that is the current observation point, or could be ahead of it, could be behind it, and so on and so forth. And the Kalman filter, which we all use, uses a state space model, and then it sort of runs the Ricardo equation for the error variance. So this is the problem set up. So when I started looking at this problem, I was just come off from a ship from Carolina's Beitwa, and we had this fire control system for firing a gun. This is actually a picture of an American system, but there was a British equivalent called FPS-5 which I worked on. And that system had an understanding of how this system actually sort of ran a very minimal version of Kalman filter. But when systems are built, Kalman filter was not known, but there are some very minimal versions. So I had an understanding of how this will function. So I was holding this in my mind when I started working on this problem. Next slide. So it turns out that at that time there was some work done in Russia called Lipston, Shiriev, and there was few results about estimation of such signals of this problem. And there are many problems I'll talk about which could be solved, and there were few results. But I started working on this, and it turned out the way to model this correctly was using, you have to use a different kind of calculus, not the normal Newtonian calculus we use, called stochastic calculus. Some of you might work in it. I was using Ito's stochastic calculus, and so it turned out that it needed lots of theoretical R&Ds and all that. And this was actually the fundamental result, which needs a lot of mathematical understanding to understand. Even I think I forgot what it meant. But it is a diffusion type equation which predicted the evolution of the density function of the signal based on underlying model. And not go back. And it turned out from this you could derive a number of results. Of course, you could derive the Kalman filter if you make it linear, and then all the Kalman filter results will come out. And they published this actually only in one paper in the Information Theory Conference, which was held actually in Israel at that time. And then I got busy we had a war with Pakistan, and I got busy with the Sona project, and never really published it further. But this had reached, my thesis reached Stanford, and there I think it was well appreciated, and Berkeley, Professor Eugene Wong looked at it. So they wanted me to come back and give a set of lectures in Stanford on this idea. But I think we in the United States were not in good terms, so the government didn't give me permission to go. This was back in 1972, I think, 73. Next slide. So actually, this particular result cracked the problem open in a very big way, because if you look at R, S, and T, if T is equal to S, it is moving forward. It's called the filtering problem, which we generally solve. If T is ahead of S, it's called fixed lead prediction, and or if R and S are fixed, and then it's called fixed interval smoothing. Lots of problems. But where I found, and these results were very few were known for the nonlinear model. But my results actually, my theory actually cracked the problem open. You can get all